Hey everyone, welcome to this month's Tech Talk, hose routing and installation, and thank you for joining us. Quick agenda here. We're going to get into some hose basics and background on hoses. Then we'll dive into proper hose selection, proper and improper hose installation, and then we'll close out with a lesson on static dissipation. So hose basics. Hose differs from tubing in that it's an assembly of multiple components, and each of these parts of a hose is critical in determining its performance in a particular application. So the core tube is the wetted surface that the media will contact. So it will directly impact compatibility, internal cleanliness, and drainability. However, it provides little to no pressure containment. In order to support the core tube, a braid is generally used to give the core tube strength. And braids can come in various materials, wire thickness and pitch angles, and those will impact flexibility, strength, or the pressure rating, temperature performance, electrical conductivity, and many other factors. And braid material can wear away due to abrasion, and it can collect dirt or grease, which could be difficult to clean. So for this reason, there's a lot of optional cover materials to improve that braid protection. And then lastly, every hose needs end connections to connect to the fluid system. So these ends are connected in multiple ways depending on the core material type. However, in all cases, the end connection method must withstand full burst pressure without separating from the bulk hose. So the four main types of hoses offered in industrial markets are metal core, fluoropolymer or Teflon, thermoplastic or nylon, and rubber core. Each has clear strengths and weaknesses, and applying the wrong hose to an application can drastically affect hose life and safety. So metal hose is made from corrugating a very thin metal tube, and these corrugations give the hose hoop strength and high flexibility. A braid is applied to give the hose its strength, and then the end connection is welded to the braid and the core tube. Metal hose is typically used in high temperature or permeation critical applications, but it tends to be higher priced and can fail sooner in dynamic applications. Think of repeatedly bending a paperclip back and forth. That's an example of how a metal hose could fail in a dynamic application. Fluoropolymer or Teflon hose is a thin tube of PTFE material that has very high chemical compatibility with nearly all fluid media. End connections are typically crimped or swaged on, which is critical that they don't separate under extreme pressures. And these hoses offer high cleanability, but they do suffer from permeation, kinking, and sometimes even impulse cracking. Thermoplastic hoses were designed for high pressure impulse applications like pumps and hydraulics. Impulses can quickly crack the core of other hoses, but thermoplastic hoses can absorb those pressure spikes and last much longer. Due to the materials used, though, the performance is greatly reduced at high elevated temperatures. And then lastly, rubber hoses typically have a barbed end connection that is pushed onto the hose. So these hoses are very easy to make, they're low cost, they can take high levels of abuse, and a lot of times they're used in many less critical applications. So hoses are typically an afterthought, and the chosen hose for an application is more times than not, it's the previous hose that just failed. So understand that not all hoses are created equal, and ensuring the right hose is selected can make a huge difference in the hose's life and for safety in the plant. So this chart shows the general strengths and weaknesses of the various hose types. A lot of times we see errors in applying the hose for a particular application. However, sometimes the situation can provide challenges. So imagine you have an impulse application, but you need high temperature also. These can make hose selection difficult, and sometimes a compromise or even trial and error is needed to get the best hose for that application. We do offer hose advising though. We have hose advisors on the team. They're trained experts in providing hose selection advice. And if you encounter difficulty selecting the right hose for your application, always feel free to contact your Swagelok Sales and Service Center for hose advisory assistance. Let's move on to hose selection. So the question to think about is, how long will the hose last? Well, hoses begin to wear out as soon as they are put to use. It's kind of like the tires on your car. So let's compare the two. And that tire's life depends on a number of variables. The quality of the tire, how many miles are on the tire, how often are we rotating them, the pressure inside the tire, the weight of the vehicle, and also the driving conditions. So as you work through hose selection, remember the STAMPed acronym. It stands for size, temperature, application, media, pressure, end connections, and delivery. So when it comes to size, you got to ask yourself a series of questions. What's the inside diameter, the outside diameter? Are there space constraints? What are the flow rates? What's the length of the hose need to be? For temperature, what's the min and max temperature? What's the ambient or the environmental temperature like around the hose? This could lead to the type of hose decision. When it comes to application, does the hose flex or twist? Is it dynamic or static? Is there vibration? When it comes to media, you need to know the media and the environment that the hose will be exposed. This will help determine the materials of construction best suited for that application and whether the hose requires certain options. So there may need to be special cleaning of the hose, for example, in oxygen systems or pharmaceutical applications, such as SIP or CIP. When it comes to pressure, what's the min and max pressures? Is it being exposed to vacuum? Are there pressure pulsations? For end connections, how's the hose going to get connected to the existing system? And can we eliminate the twisting by converting from NPT to a tube adapter so it can be positioned properly, then installed? What end connection will give the hose the best functionality? And then lastly, on delivery, how fast do you need it? Was it needed yesterday? Should there be a stocking strategy to reduce or avoid downtime? There's lots of questions to ask, but keep the STAMPed acronym in mind so you can address all these specifications and can select the right hose for your application. So these next couple of slides show examples of selecting the right hose and realizing large savings or safety improvements with the proper selection. So back to the tire analogy. No one really buys a car and expects a tire to last forever. All of us have a mental idea of a preventative maintenance plan for our tires. You inspect them, you repair them, and of course you replace them before a failure causes a major issue. Hoses are the tire of a fluid system, yet very few companies have a PM plan for their hoses. Hoses need to be inspected. They need to be replaced before they become a major problem. So similar to tires, the length the hose will last does vary based on the application. And hose suppliers and experts can provide guidance, but keep in mind that every situation is different. Preventative maintenance programs are essential for hoses. So creating a PM program at a major biopharm company saved that company over $500,000 annually in unplanned downtime and maximizing the hose life. Hoses are handled a lot. They're actually one of the most commonly handled components in a fluid system. The flexibility allows them to act as a handle in dragging a connection from one port to another. So they're commonly grabbed and they're commonly touched. So many times these hoses have hot media like steam running inside of them. And the metal braid absorbs this temperature and can transfer it very quickly to someone's skin. So the picture on the left shows a steam tattoo. It's a burn that occurred when an operator leaned against the hose that was over 400 degrees Fahrenheit or about 200 degrees C. Now, furthermore, moving a hose around, it can rub the external braid. It can tear or break those wires from that braid. These wires are very thin and they can feel like needles if they're grabbed or rubbed against. So handling hoses can be a significant safety issue. And for these reasons, many suppliers of hoses offer accessories that improve hose safety. insulation material, abrasion-resistant wraps, and sleeves. Those are some of the examples of options that should be considered when a hose can come in contact with your personnel.
So now let's discuss hose installation. Proper routing is key in overall life cycle of a hose, and these pictures show examples of unsuccessful installations. So poor routing, which includes selecting the length of a hose, is clearly the leading cause in hose failures. The most common result is a kinked hose, which causes permanent damage, but it can also lead to more significant damage from moving equipment or crushing the bulk hose core or even pulling a hose out of an end connection. Not only are these issues costly for needing to replace the hose, but they can become major safety hazards for work environments. So we've all probably seen a kinked hose before. And bending a hose actually causes the cross section to turn oval. And this ovality bends the sides of the hose to the point where the material stretches beyond its elastic limit, and it results in plastic deformation. This means that the hose core walls have been permanently damaged, and even if the hose is straightened and the kink is massaged out of the hose, the material is permanently damaged. So with a garden hose, this isn't a major concern because the hose only contains water and it's at a very low and safe pressure. But for industrial hoses, a kink means that the hose will no longer maintain full working or burst pressure, which can lead to very dangerous situations. The most common cause for a kinked hose is incorrect length in a dynamic application, but it can also be a result of poor routing or physical abuse of the hose. Let's talk about minimum bend radius and how it determines when a hose is kinked. So every hose supplier should be able to list a hose's minimum bend radius, or MBR, for static and dynamic applications. So for static applications, the MBR is the smallest radius the hose can achieve without transitioning to that deformed state or when there's permanent damage. For dynamic applications, the hose is tested at full pressure and cycled in a dynamic motion for 10,000 cycles. A dynamic MBR represents the smallest radius that the hose can be bent to, but still maintain full pressure during these cycles. The most common spot on a hose where kinking occurs is at the end connection. And this is due to improper length. There's actually weight pulling down the hose as seen in the picture on the left, or there's excessive motion in that application. So it's always recommended to allow for a straight length of hose that's at least 2 times the outer diameter before starting any bends. Again, you want a straight length of about 2 times the OD before starting any bends. Now you don't need to force that length to be straight because as hoses typically have a preset bend to them, but this rule allows for some extra length to relieve stress at the end connections. So the goal of this slide is to not teach equations that are seen, but really to let you know that there are industry standard equations out there that we follow to help determine proper hose lengths. So hoses are used very often in dynamic applications that have repetitive motion. So many times the hose length is determined without the full range of motion in mind. And this can lead to kinking, it can lead to stretching, or rapid failure of the hose. Dynamic bend radii should always be larger than static, as the hose is put through extra strain during that constant motion. So there is a standards organization, NAHAD, or the North American Hose and Accessory Distribution, and they developed these set of equations that guide users to determine the correct length of hoses for these dynamic applications. Swagelok hose advisors and field engineers are trained in these equations, and we can help you determine the correct hose length for these applications. Even in static applications, hoses fail over time due to improper routing, causing strain at the end connection. And a very common example is shown in these pictures. So the hose comes out of a wall or it comes out of a fitting horizontally, and gravity constantly pulls down and bends the hose at the end connection. And although this may seem minor at the time of install, gravity's pulling on the hose 24/7, and it will slowly cause damage at the end. Furthermore, if you have a liquid media that's running through the hose, the additional weight inside the hose will speed up this kinking process. So a simple fix is to add an additional elbow fitting. It's enough to eliminate that strain, and it provides far longer hose life at a very minimal cost. Now, of all the issues we just discussed, dynamically bending a hose in multiple planes will tear apart a hose the fastest. So imagine a hose with one vertical connection and one horizontal connection, but they're offset from each other. So this hose is considered to be bent in two planes. You can't take that hose and place it flat on a table. So although a static hose bent in multiple planes could live a long and healthy life, if one of these connections is dynamic or it's moving, the hose will fail very quickly. The dynamic motion causes a twisting motion in the hose, which will either twist the barbs in the end connection, or it could twist the core material of the hose, and either of these will rip apart the hose. In nearly all cases, a dynamic two-plane bend is the result of someone wanting to do a quick and easy installation. So these can be fixed with splitting the routing into a static portion and then a dynamic portion. So on the picture on the left, the static hose brings the dynamic hose up to the same plane as the dynamic port. So if we can, avoid two-plane bending of hoses. Let's talk about static dissipation. So have you ever shuffled your feet across a carpet, especially now or in the winter months, and then reached for a light switch, or pulled apart two wool blankets with the lights off? You're creating and releasing a static charge. The same thing happens to hoses. And this is the second highest reason for failure after kinking. So gases and liquids flowing through hoses, they deposit electrons on the inner core of the wall due to friction, and that creates a static buildup. So this isn't a problem in metal core hoses because the static charge simply flows through the hose material. However, in softer core materials like a Teflon, the electrical resistance is basically infinite. It's extremely high, which means that the static charge remains on the inner core of the hose. So what happens is eventually that charge becomes high enough that it needs to jump to the closest conductive material, which in many cases is the metal braid on the outside of the hose core tube. And just like your finger up to the light switch, it creates a spark, which is a little lightning bolt that burns a small hole into the hose core. So these pictures show the burn marks from static charges jumping through a PTFE core to the external braid. These hoses were both sent back to us for evaluation, and the cause was due to small pinhole leaks. So many factors go into whether or not a hose will experience issues with static charge. One is what's the media? What's flowing through the hose? Some gases and liquids deposit electrons very easily, and some don't do it at all. So we can help determine how likely this will be due to our experience with the problem. But you'll notice from this list that more hydrocarbons and steam are the main offenders. Another factor to watch out for is flow velocity. So similar to shuffling your feet faster on a carpet, a faster media flow will cause static buildup in a hose to happen more often. Then you have other factors like humidity and temperature that could turn this issue on and off within a hose application. But the bottom line is, if you're using a non-metal hose with a media that could cause static buildup, you should plan on dealing with this when selecting your hose. So the definition of a static dissipative hose is the inner core tube of the hose has the ability to dissipate a static charge without creating a spark. Metal hoses are all static dissipative by nature because of the conductivity of the metal, but softer materials are not, and they need help in doing this. And a common and effective way to do this is to add a carbon material infused into the actual core material, into the Teflon, And even though this carbon gives the core a black look visually, which can be confused for being dirty, it's infused inside the core. And through all of our testing, we've never seen a difference in cleanliness between the carbon-filled cores and the standard Teflon cores. And what the carbon does is it allows a small flow of current. There's electrons flowing either through the core to the braid or down the core to the end connection, which dissipates the static buildup. Basically, it makes that electrical resistance of the core less than infinity. So the picture on the left shows a set of hoses that were returned to us with pinhole leaks marked with the yellow tape in all those different areas. And these hoses were in service for over a year without any issue. And then one day the customer decided to increase the flow rates to improve production output. Well, that was one of those variables, which was flow rates. Turn that up, there's a higher likelihood that you can get that static buildup and static charge, and that's what happened in this scenario. So we've seen in some cases where people refuse to use carbon core because the hose needs to be non-conductive. Now, a hose with a metal core or a metal braid is conductive in that it allows the large flow from one end to another. But in the case where the two ends need to be isolated, they need to be electrically isolated from one another, the hose needs to be non-conductive. So on the picture on the left, this hose has a nylon non-conductive braid and a carbon-filled Teflon core. So if you run a current through the hose, it shows that the carbon core results in about 80 mega ohms of resistance there. It's less than infinity, yes, but it's still extremely high. And this high resistance does provide enough current to dissipate static, but it is not considered to be conductive. Okay. In the example on the right, the hose is a metal core and it has a metal braid. And the resistance there is 0.4 ohms, which is a lot less. It's about 200 million times less than the resistance on the hose on the left. So if you have the same voltage, this hose would provide 200 million times more flow, electron flow. This hose is conductive, and it's also static dissipative. So the bottom line is, do not let the needs for a hose to be conductive or non-conductive cloud your decision to get a static dissipative hose. So to sum up static dissipation, understand what media you're using and the likeliness of that causing static charge. When in doubt, use a carbon core Teflon hose. And just because a hose dissipates static, it does not make it conductive, as we saw in the example between the metal core and the PTFE carbon core. And in conclusion, 1, understand which hose type is best for your application. 2, plan for safe and efficient routing of the hose, especially in those dynamic applications. And know when your hose needs to dissipate static charge. So thank you. And if you have any questions, go ahead and ask them now. And lastly, you can join us for our next Tech Talk, which is next month. It'll be on regulator basics. That's Wednesday, February 17th at the same time between 11:30 and 12. Hope to see you there.